Hey guys, welcome back to my channel and good evening. Today we're going to talk about the graphs. So far we have been looking at um, trees, data structure, especially binary trees. And we were talking about methods to traverse that trees, including BFS, DFS, um, and also we were looking at binary search trees, how the left side of the subtree is always lower than the root, and right side of the subtree is always higher than the root, its values, I mean. Now we're going to look at the bigger picture, um, like I explained when I was first going through the DFS, which is called the graph. So graph data structure is basically consists of nodes and edges. So I'll just share the important terms in this data structure. Today I even made a word list. So that's a big improvement from my crude representation. But anyways, so yeah, for the nodes, you can also turn them as vertices. So it's the same thing. Um, like for example, if you see a shape of rectangle or square or a triangle, I'm sure you have heard of vertices, the points in between the edges, and those edges are lines in those cases. So yeah, let's say for triangle, there are vertices, also called as nodes in this kind of data structure, and they're connected by edges or lines. And in a graph data structure, there's directed edges and undirected edges. Directed edges are something like binary trees, something that binary trees uses. So um, the only from one vertices to another can the edge flow. So binary tree, like for example, only from root to its children, it can move, right? But it cannot move the other way around. Um, and that's always the case for a binary tree. Whereas in graphs, there are multiple nodes, and sometimes it can go back to where it came from. So in that case, that's undirected because um, yeah, you can go back to where it came from, and it doesn't have a direction, specified direction. So that's what it means by undirected edges. Uh, Connected components. It's when I'll also use paint. So let's say that for binary trees, there are roots and its children nodes. But in this case, there's only one connected components because all the nodes are connected to each other. So for instance, from the children of the children node, this can go to the root. I mean, it cannot go literally to root because it's a directed type of graph, but you know what I say. It's all connected, all connected. So this type of graph is called the connected components because there's only one component. But let's say that there are nodes like this, and then there are nodes like this, and it's a one graph. Then from here to here, there's no way to jump over, right? So this is one type of connected, this is one connected component, and this one is another connected component. So there are two connected components in this graph data structure. So that was pretty clear. Degree of edges is the incident of edges that can flow into one vertices or nodes. So or outside. So let's say that there are nodes and there are millions of nodes, more than this, flowing into this one big node. Then these are called in degree. And when it's going outside, this is called out degree. So yeah, in and out. That was also pretty simple. Neighbors are just the literally the node that's right next to each other and connected. Uh, these are all neighbors. Cyclic is when the nodes path are all connected like this. So whatever it does, it infinitely traverses through these two nodes. So if in a graph data structure, if this kind of incident happens, like it infinitely goes through each other, if, if any one of this exists, then this whole graph is called cyclic. But if this doesn't exist, then it's acyclic. So yeah, that was a basic terminology for a graph data structure, and it was pretty simple. Now, what's not simple about graph data structure is that compared to linked list, where the head is given, and binary trees where roots and all the nodes are given, um, and when you want to traverse them, for instance, in a binary tree, you just select the left side or right side of the node. You specify the reference and you just traverse them. That was pretty easy, but uh, for a normal graph data structure, you cannot do that. And there are specific input formats in which the questions are going to give it to you, including matrices, array of edges, adjacency metrics, all sort of those different input style. And it's our job to make sure when we look at the question, including nodes, because the graph or binary trees are always going to come with this kind of yeah, nodes. If they're going to ask us to use those kind of data structure, it is our job to identify that it is a graph data structure. Um, and one way to do it is, of course, looking at the input format. Um, and also um, because we cannot really simply reference the node left, node right, and like binary tree, and um, um, it's not a directed graph like binary tree, so it's undirected. It can go back to its parents. We have to use a certain way in order to um, um, for any given node, we can immediately access the neighbors of its node. Um, okay, for instance, let's start with array of edges. So let's say that there are some arrays. Yeah, like this type of list with all the edges nodes given. Its input is a 2D array. So each element is in the form of list X and Y, bracket X and Y, which indicates that there is an edge between X and Y, like 2 and 3, 2 and 3, 4 and 2. And these edges can be directed and undirected. Um, because we cannot mm, so why cannot we so my point is why can't we immediately start traversing? Because if we want to start depth first search from node 0, um, you need to uh, when we are at node 0 or node 2, how do we find its neighbors? We will need to iterate over the entire input to find all the edges that include this 2. And when we move to a neighbor edge like this, after traversing this, we will need to iterate over the entire input again, starting from the start, to find all the neighbors of that node, of this specific node. So at every node, we would have to iterate over the entire input, and this is going to cause so much time complexity, and it's going to be very, very slow. So what we do is just like what we did when we used HashMap, to use a HashMap, basically, like a set data structure in the Python. Um, so that's kind of a pre-processing that we do before going through the nodes and putting it into uh, a set so that we can easily find the neighbors of all nodes. So, hmm. So we can iterate over the input for each of these XY pair, and we can put Y in the list associated with graph um, X. If the edges are undirected, then we will also need to put X in the list associated with graph Y. So after we build the hash map, then we can do graph 0, and then we can find, or 2, and we can find immediately all the neighbors associated with this node 2. Um, so this is like this example code that would mm, build the graph from array of edges. So that would be if graph building graph edges. We first build a hash map, so that would be default ticked in Python, and a list of edges. Then we specify it into a variable. Now for X and Y in edges, graph X dot append Y and graph. Okay, we do this if the graph is directed. So if it goes one way from X to Y, but if it also goes from Y to X, we would also have to specify that, and we would have to also write this graph Y dot append X. So it makes it undirected, it goes both ways now, and we return graph. And this will make a simple graph data structure between X and Y. So that was pretty simple, and that's like the basic when the list of edges is given for this kind of graph data structure. Now, it's 11:40. We have to be quick. Now, there are second data type that would be adjacency list. So from adjacency list, the nodes will be numbered from 0 to n-1. And the input will be a 2D integer array. And it will also be called a graph in this case. And graph I will be the list of all the edges that's going out from this ith node, list of all the edges. Okay, and this is like the example of the adjacency list that can be provided as an input, and that's like one, two, something like this, right? So we can immediately access all the elements, all the neighbors of the inner elements, immediately access it without any pre-processing, like the hash map that we use for the array of edges. So that makes it a preferred type of input format for this kind of questions, graph questions. Because like, for example, graph 4 would mean that we want all the neighbors of node 4. We just check this specified graph 4. So yeah, that was the second input format. The third input format is adjacency matrix. So once again, the nodes will be numbered from 0 to n-1, like adjacency list. And you will also be given a matrix of a size m times n. And graph, in this case, will be specified as graph I j equals 1. So this is a row and this is a column, right? I is a row, j is a column. Usually that's also in linear algebra. And in this case, it means that there's outgoing node, outgoing edge from node I to node j in this kind of adjacency matrix. So yeah, everything else is pretty much the same as the adjacency list. When you're given this format, you have two options. One option is that during the traversal at any given node, you can iterate over the graph node. And if this graph node I is 1, then you know that this node I is a neighbor. So when we are, once again, when we're traversing over this graph node and we check this ith node, and if it's equal to 1, that it means that I is a neighboring node. Also, you can pre-process this graph. So it's not the same as adjacency list, like using a hash map. and then you can graph it. If here from graph ij, so the ith node to jth node, the edge connecting that is 1, then we put this j in the list with the key of graph I. So in this case, key is graph I, and the value is 1, right? No, value is j. Value is j. Yeah. So, and this key and value is just, we're using that because we're thinking about Python's dictionary type. So, and then the benefit of using this method is that when performing the traversal, you don't need to iterate n times at every node to find the neighbors. And this, both methods will have the time complexity of n squared. Okay, yeah. So that was adjacency list, and this was adjacency matrix. Now, last format is the matrix. This one, I was told that it is a lot more common. So the input will be a 2D matrix with I and J, and each square will represent something, and the squares will be connected in some way. So basically, just like linear algebra, row and column, and of the matrix is a node, so row and column, and the neighbors are row minus 1, column, or row, column plus 1. So just right next to each other, the nodes right next to the specified row or specified column is a neighbor. And the nodes in these graphs, when given a matrix, is not numbered from 0 to n. Instead, each element in the matrix represents a node. The edges are determined by the problem description, so you'll probably find it in the problem. So yeah, probably it's best explained through solving examples, which I'm gonna go do tomorrow. What else? What else is there? What time is it? 11:45. Let's quickly then go through the difference between binary tree, graphs, and trees. So first of all, binary tree has a root node to start traversing from, while graph doesn't really specify that. It doesn't really have an obvious start point. The second difference is that binary tree, we have the object for the node, and each node has a pointer to its children. So it's children node. But in a graph, we don't really have that kind of thing, also because the same reason that we don't have a starting point. Within a graph, because there might be a chance that we might go through the same node again when we are traversing, because it's not a, like I said, it's not a directed graph, it's undirected. So it just doesn't go flow the one way. There might be a chance that, but okay, this children or parent node saying this in a graph is inappropriate, but there's a chance that the child node might visit parent node again, and the other child might visit the parent node as well. So in that case, the parent node can be visited twice. One way to avoid this is by using a set in Python, and that's pretty simple because sets removes the ones that are duplicates. Um, but like I said, yeah, the difference is simply that in binary tree, this doesn't happen. Yeah, I think this is about it. Today we looked at the basic terminologies and different input structures for the graph, not the structure, but input types for the graph, adjacency matrix, adjacency list, matrix, and list of edges, and how to deal with the list of arrays. Uh, Tomorrow, we're going to solidify this knowledge by trying out some questions, one or two. Hopefully, my brain holds up. And if not, I'm going to simply go through the answers. Best way to solve the question, for me at least, because um, yeah, I cannot just sit there for 3, 4 hours. It's the way is not for me. I was told by my mentors and some of my teacher that I should just sit there and then solve the question for hours and hours until it comes to me. I tried it, but it never came to me. So for me, it's more efficient. If I cannot solve it, I just go straight away to the answer. Try to figure out how it works and then implement it myself at least. And yeah, that was it for today, guys. And thanks for listening. I'll see you guys tomorrow.